My name is Yasaman Yazdi, and I'm a postdoctoral fellow at the Dublin Institute for Advanced Studies in Ireland. And my area of research is the causal set theory approach to quantum gravity, which proposes that the fundamental underlying structure of space-time is a discrete structure called the causal set, which is a type of partially ordered set where the sets of elements are the space-time elements and the ordering relation among them is the causal precedence relation, so which elements are in the causal past of which other elements. Causality or causal structure is a very important aspect of all of physics and especially gravitational physics. Much of general relativity, which is our current leading classical understanding of gravity, actually relates to causal structure, or which points of space-time are in causal contact with which other points in space-time, which is limited by the fact that nothing can travel faster than the speed of light. So the information contained in the causal structure of a space-time is almost enough to tell you everything about a space-time. It's most of the information about a space-time, except that there's one missing piece. So to know everything about a space-time, you need to sort of know if any pair of elements in a space-time are causally related or not. But then you additionally need to know, in some sense, how far or how close they are to one another, whether or not they're related. So there's an extra scale information that you need as well. But the causal structure information already gets you far in explaining a lot of things. But in addition, you need the scale information, which in a discrete setting can be provided in addition to the causal structure part. Causal sets are what we imagine to be the fundamental underlying structure of space-time. So the sets in causal sets are the set of space-time elements, and there's in addition information about which elements are causally related to which other elements. So as we saw, causal structure gets us very far in recovering information from a space-time, but in addition, we need some scale information. So we need to know which elements are causally related to which other elements, but in addition, we need to, in some sense, know how far apart or how close these elements are to each other. And it turns out that we can use the sort of number of relations between every pair of elements to recover even that scale information. So because we have discreteness, we can actually count. So we have a pair of elements, we see are they related or not. And then in addition, we can count how many relations are between those elements. And that'll give us the extra scale information that'll then help us recover all of the important information about a space-time. There are some powerful theorems from the 60s and 70s by people like Hawking, Malamud, and Zeeman that tell us that given information about causal structure, and in addition, this extra information about scale or volume or distance, how far or close elements that are related or not are to each other, we can recover the full information about a space-time. Now, in causal sets, we take that to heart, but in addition, we introduce this extra feature of discreteness because we hope to go beyond classical GR and address quantum gravity questions. And discreteness is a very natural feature to incorporate into our structure that's going to be more fundamental than the continuous Lorentzian manifold and metric of GR, because all sorts of problems occur when you go to very small scales, all sorts of UV divergences and things that don't make sense about smooth manifolds and smooth spacetimes. So we want to incorporate that discreteness in there, but we also know that this, causal structure and the scale information is something that we need to retain in order to then macroscopically or in the classical limit recover everything that we know about spacetime and GR. So these theorems tell us that causal sets as a structure are rich enough to recover all the information about a space-time, but they don't actually tell us how to do that. So it's a very active area of research to actually figure out how to recover all the different features of a space-time that we're familiar with, and especially starting with ones that we think are important, like things like proper time, space-time volume, and so on. The first step, even before dynamics, is to understand the kinematics. So what do we even mean by a causal set looking similar to or being approximated by a space-time? So the way we think about that roughly is that a causal set approximates or resembles or corresponds to a space-time if it satisfies the following rough properties. Firstly, that the causal relations in the causal set should reflect the causal structure of the space-time that it is said to be approximated by. Secondly, it needs to encode the volume information, which is where we're going to get the extra scale information on top of the causal relations from the causal set. And then lastly, we only expect this discrete causal set to resemble or correspond to a more familiar continuum Lorentzian spacetime metric and manifold at scales beyond the discreteness scale. So close to or at the discreteness scale, it's going to look nothing like a spacetime manifold. So once we understand what we mean by causal sets that can look like spacetime manifolds, we can go about constructing those causal sets. And a very sort of practical way to do that, again at the kinematic level, is using something called a Poisson sprinkling, which we can think of as taking a given spacetime manifold and breaking it up into small subregions with subvolumes, let's say dV, and then placing a point in each of those subvolumes with some probability independent of each other using a Poisson process. Then in the limit of these subvolumes going to zero size, we recover something called the Poisson distribution, which turns out to be the best way to place a finite number of elements in a spacetime manifold to recover the volume information of that spacetime manifold. And then we can give those elements that we placed in the manifold the causal relations according to the underlying spacetime. So at a kinematic level, this procedure would give us a causal set that satisfies the properties that it would take for us to say that it approximates a given spacetime manifold. It has the causal relations of the spacetime. It has the volume information to the best of its ability, meaning that it recovers the volume information with the smallest standard deviation, and it looks like the space-time at scales bigger than the discreteness scale. So then the next step is we can try and think of how to dynamically construct such a causal set. And the dynamics is very much a work in progress, but we have some models out there called classical sequential growth models. And the basic idea is to think of these causal sets growing as a process. So first you would have the first element of the causal set being born, and then subsequent elements are born after that, satisfying a set of rules. And these rules, in simple terms, are sort of constructed to obey causality and also a discrete version of coordinate invariance. So if we could sort of build a causal set using a different sequence of adding these elements, those should be physically the same. Ultimately, yes, the problem of quantum gravity is to have a quantum dynamics of space-time, or the more fundamental structure that's going to replace it. Now, of course, we're not there yet. We and anyone in any other approach, it's a very difficult problem. but I think it's also really important to spend time thinking about the kinematics and the classical dynamics once your starting point is drastically different from the starting point of classical GR, which is the case in causal set theory. We're replacing a classical smooth Lorentzian manifold and metric with a discrete, fundamentally discrete causal set, a partially ordered set. So the set of mathematics and conceptual questions and physics that comes along with that, even at the classical level, is dramatically different from GR. And also even in between sort of classical theory and the full quantum theory, there is a lot of semi-classical physics that we can think about. We can think about doing quantum field theory on these classical space-times, and already there a lot of things change because of the discreteness and the non-locality, and again the inaccess to differential operators. So we have to rethink a lot of those things, and we should carefully do that, which will sort of inform the approach to the full quantum dynamics, which of course is being done in parallel, but it's very non-trivial even to just go back to the physics that we already know and rethink it through the lens of these fundamentally discrete causal sets that have different qualitative and quantitative features. The focus of causal sets has been to understand the quantum nature of gravity. The focus has not necessarily been to include matter, and the perspective is not necessarily that insight is going to be crucial to understanding the quantum nature of gravity. Nevertheless, we have some interesting formulations of quantum field theory on causal sets, and some very interesting insights have come out of that. From a perhaps more phenomenological perspective, you can view the causal set as the best possible regulator of any quantum field theory, because causal sets are intrinsically covariant or frame independent, because you can think of each of the elements of the causal set as a unit of spacetime volume, and spacetime volume is a coordinate invariant, diffeomorphism invariant quantity. So it's the best way to regulate it's the best way to regulate things. And quantum fields have all kinds of UV divergences. So it's interesting to ask whether you can regulate those quantum fields using the discreteness of causal sets. And it turns out that you can, because oftentimes, especially for free fields, you can describe most of the physics using what are called green functions of the quantum fields. And these green functions are very closely related to the causal structure. So these are ingredients that very naturally live in the causal set and can be constructed and understood using basic quantities in the causal set. So using that, we have constructed some free scalar field theories that are defined on the elements of the causal set and are finite everywhere, and we can study all the usual effects that we like to study in quantum field theory and curved space-time, except instead of having a smooth background, we have a discrete causal set background. So a lot of quantities that are natural or intrinsic to the causal set are combinatorial in nature, and that means that we're counting things, often relations of some kind. And then the way we extract geometric information out of these combinatorial quantities is statistical. So we would have, for example, some function, some causal set function that we think of as macroscopically corresponding to some geometric quantity. And this function would map from a causal set to the real or imaginary or complex numbers. And then we would consider a whole ensemble of, for example, causal set sprinklings of a given spacetime manifold if we're interested in a particular context, like flat spacetime or black holes or cosmology. And then we would consider the average of that causal set function over this ensemble of causal set sprinklings. So it's a very statistical in nature study. And the direct way to do this would be quite numerical, because the causal set is an intrinsically discrete object. But there are also methods to map these more numerical calculations to analytic ones. So there's combinatorics, statistics, and a lot of numerical mathematics. In fact, there are a whole bunch of causal sets that don't look like any space-time manifold at all. The most dominant class of such, as we call them, non-manifold-like causal sets, are called the Kleitman-Rothschild partially ordered sets. And the reason why they don't really look like any space-time manifold is because they exhibit something like 3 instances of time. And that's not really something we expect to see in a space-time manifold. So they have this very discrete, non-geometric feature to them, and they're also very highly connected. And there are a bunch of other related non-manifold-like causal sets. So it is a problem of the dynamics to differentiate between these non-manifold-like causal sets and the manifold-like ones. But of course, perhaps at the very early universe or at the center of a black hole, there is some non-trivial role to be played by these non-manifold-like causal sets as well. But in terms of the manifold-like ones, at the kinematic or phenomenological level, we can, in principle, study any causal set resembled by any space-time manifold that we like, using this Poisson process of constructing causal sets that are approximated by or correspond to given space-time. Now, depending on how complicated the space-time is, how much curvature there is, what symmetries there are, what dimension we're in, it's computationally going to be a more or less difficult task. But in principle, it's the same procedure of Poisson sprinkling a given space-time manifold. And of course, there's also physical considerations to bear in mind. We're not necessarily interested in studying any space-time out there. The most interesting ones are black holes, cosmological ones, and perhaps flat space-time. Black hole thermodynamics is one of the biggest clues we have to what is really going on with quantum gravity or semi-classical gravity. We have things like black hole entropy, Hawking radiation, the information puzzle, and all of these concepts seem to be pretty rigid. They have been found and derived in many, many different ways, yet at the same time, we don't really understand them. So for example, black hole entropy, in the case of black hole entropy, we know that black holes, as with any other event horizons, have an entropy associated to them that is proportional to the area of their event horizon. But really understanding this from a more microscopic or statistical mechanical perspective has been really, really difficult. So this would be something like, what really are the degrees of freedom that are contributing to this entropy? Are they internal states? Are they entangling states? Are they due to matter? What really is going on? And one of the most promising directions to understand this microscopic origin of black hole entropy is entanglement entropy, which was in fact created or thought of in 1983 by Raphael Sorkin, precisely in the hopes of understanding the microscopic origin of black hole entropy. So entanglement entropy, too, generically scales as an area, or as we call it, an area law. So it scales as the spatial area of the boundary of an event horizon if we're in a space-time with an event horizon, or more generically, the boundary of any other division that we make in a space-time. But this area law scaling is in terms of a UV cutoff. And there are many, many different ways of defining a UV cutoff. And that has been one of the reasons why it's been very difficult to understand what is really the right UV cutoff or the right way to think about the microscopic origin of this black hole entropy. So for example, if you imagine the stationary black hole sitting there and you are an observer outside this black hole trying to understand the microscopic origin of this black hole entropy, you have a hypersurface associated to you, and you may want to think about the quantum degrees of freedom or modes of a quantum field or something like that that'll somehow count this entanglement entropy for you. But you have to somehow decide how you want to count these degrees of freedom, and you may use your proper time or your coordinate time. Depending on what observer you are and what choice you make, you're going to get a different answer. And even if you have your favorite way of making a decision in that case, once you go to a different setting, let's say the black hole is rotating or you're in a cosmological horizon, you have to yet again make that decision. So then it becomes really difficult to unambiguously say what is the right way to count the degrees of freedom in these different situations. It's difficult even in a given situation, but it's even more difficult in different situations. Now, in causal set theory, there's a clear way to do this in all of these different scenarios, because the nature of the UV cutoff or the discreteness is exactly the same in any scenario, whether it's a causal set that's approximated by a stationary rotating black hole, a cosmological horizon, an accelerating observer horizon. It's all the same. It's just one unit of Planckian volume or super Planckian, sub-Planckian volume. It's just the discreteness based on the spacetime volume. And this has the very same meaning in all of these different scenarios. So it gives us the hope to sort of understand this microscopic origin of black hole entropy and horizon entropy in an unambiguous and meaningful way. So that's something really powerful that one can hope to achieve with causal sets, and that we're working hard to achieve. So one of the most interesting and important results to come out of causal set theory is the ever-present lambda cosmological model, or the ever-present lambda dark energy model. And the basic idea behind it is that the value of the cosmological constant lambda fluctuates both in sign and in magnitude. And it is at all times statistically of the order of 1 over the square root of the space-time volume of the observable universe. So in a scenario like we think we live in 4 dimensions and in a space-time that's roughly something like an FLRW cosmology, that would be something like of the order of the Hubble parameter square or the ambient energy density. And the model is called ever-present lambda because the cosmological constant is always of the order of the ambient energy density, or always related to the size of the universe in this way. So it's always a relevant energy scale and has something important to say about the evolution of the universe. Now, the reason that we get this relation is connected to a couple of things. One of them is the fact that the cosmological constant and the spacetime volume are quantum mechanically conjugate variables if we think of something like a unimodular gravity type of scenario, which is essentially something like assuming a fixed spacetime volume constraint on an approximate gravitational path integral. So if we do this, we arrive at a quantum mechanical conjugacy between the cosmological constant and lambda. And having this fixed spacetime volume constraint on the gravitational path integral is sort of analogous to how we fix an interval in time in ordinary quantum theory, and we sum or integrate over all possible paths within that interval. except that in the causal set, it's the space-time volume that plays a similar role to time. So as time passes, the causal set is growing in size, or conversely, as the causal set is growing in size, time in some sense passes. So the size of the causal set plays a similar role to time, and that's why it's a natural thing to hold the space-time volume fixed in a gravitational path integral, and this is also called unimodular gravity. Now, the other important piece of information that leads us to ever-present lambda is the statistical correspondence between a causal set and spacetimes that we think are approximated by them. And we know that this correspondence is best achieved using the Poisson distribution, or the Poisson process, that gives us a causal set that has its elements distributed such that there's a correspondence with the continuum that satisfies the Poisson distribution. So if we put together the statistical correspondence and this conjugacy coming from the unimodular gravity, it leads us to this ever-present lambda relation. Many different potential explanations of the value of the cosmological constant involve some kind of UV-IR mixing. So you need some information at UV scales and some information at IR scales to understand that small value of 10 to the minus 122 in Planck units. Now, in this ever-present lambda case, indeed that's the case. So this model depends on the microscopic structure of space-time, or the discreteness of causal sets, and the statistical correspondence that arises from the nature of that discreteness and how we think of space-times that are approximated by that. Yet at the same time, the magnitude of the effect of that microscopic discreteness on the value of the cosmological constant is set by the size of the universe. So we need information both at the UV scales, or this type of discreteness and how it corresponds to the space-time using the Poisson distribution, as well as the volume of the universe, or the observable universe, to tell us the impact of, or the magnitude of, the effect of that discreteness on the value of the cosmological constant. Now, this conjugacy that we get from both the statistical correspondence and the unimodular gravity scenario is a relation on the standard deviation of the cosmological constant and the spacetime volume. And we have what the standard deviation of the spacetime volume is from the statistical correspondence between the causal set and spacetime. Therefore, we know the standard deviation of the cosmological constant. But we still need to know what the mean value of the cosmological constant is, so that we can say the value of the cosmological constant is roughly the mean plus or minus the standard deviation, statistically up to 1 standard deviation. Now, what that mean value of the cosmological constant is still an open question in this model. There are some indications from Euclidean path integral arguments that 0 is a natural number, but it is still an open question, and we still need to come up with a Lorentzian argument for that. But if we go ahead and assume that the mean value of this fluctuating cosmological constant is indeed 0, then up to 1 standard deviation, it is indeed of the order of 1 over square root of spacetime volume of the observable universe, which, if you plug in the value of the observable universe, today you get indeed the right order of magnitude for the cosmological constant, which is 10 to the minus 122 in Planck units. And what's really remarkable about this idea is that it was proposed back in, I think, 1987, which is a few years before we had the supernova observations that told us about this value of the cosmological constant, which led to all these cosmological constant puzzles that we are still grappling with today. So in a way, you could say that everpresent lambda predicted the value of the cosmological constant even before we had these observations that told us about this very unnaturally small and non-zero value of it. I think there's a lot of exciting work to be done with everpresent lambda. So the basic idea of everpresent lambda tells us that the value of the cosmological constant fluctuates in sign and in magnitude and is at all epochs of the order of 1 over the square root of the volume of the observable universe. But the basic idea isn't really enough to build a model that tells us about how the value of the cosmological constant at different times relate to each other. So we need a bit more input to build the phenomenological model and have a whole history of dark energy or this fluctuating cosmological constant to really be able to go out there and check with all the high precision cosmological data that we have out there. So we have a few simplistic models out there, but there's a lot of room for more sophisticated models and refinements of those models. And there are at the same time a lot of issues and open questions in cosmology that would be exciting to tackle with these more refined ever-present lambda models, because they have all the qualitative features to help with a lot of the open questions in cosmology today. For example, a recent thing that has come up, for example, in the DESI observations, are indications for a preference for dynamical dark energy over the simple lambda CDM constant model. Now, ever-present lambda is very naturally a dynamical dark energy model because it varies as the volume of the observable universe varies. Another issue is the Hubble tension, where there are disagreements between the value of the Hubble parameter predicted from measurements of the CMB and more late universe observations from supernovae, Cepheid stars, and so on. And again, there are some ad hoc models out there of early dark energy, dynamical dark energy, that partially address these, but we need to do better than ad hoc models. We want well-motivated models. And models like ever-present lambda provide the hope to both learn something about quantum gravity using cosmological observations, and at the same time understand cosmological observations better in a well-motivated way. So I think that's an exciting area in the near and far future. There are a lot of accessible papers out there that you can read about causal sets. Also, feel free to reach out to any of the authors of those papers. The causal set community is a very friendly one. We're always happy to talk to anyone who's interested in causal sets, has any questions, thoughts, comments. And there's also a lot of projects and work to be done for all levels of students, postdocs, and researchers. So feel free to reach out to us. And yeah.